Welcome students. Today we will discuss about lanthanides. Before going to discuss the lanthanide series, we should to know about something the periodic table. This is the periodic table. You can see there are the groups and the periods. So if you see here in a yellow color, we will get element cerium. It start from cerium and it's end at lutetium. So in the third B group and in the sixth period of the periodic table, all these elements are placed together. The first element is the lanthanum, which having atomic number 57, and the series start lanthanum to lutetium. Total 15 elements are included in this group. So all these elements have similar chemical and physical properties. And the first element is the lanthanum. So series are called as the lanthanides. You can see the 15 elements are there. The element lanthanum having atomic number 57, then cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, and lutetium. Actually, lanthanum is not the lanthanum elements, but even also it includes in this series because it shows the similar properties to the rest the elements. Now we will see the color of the lanthanides. The elements can show, the matter can show the color when they have the uh, half-filled orbitals or they absorb the light from the visible range. The color of the lanthanides emerge from F to F transition. That means there is a small energy gap between the F transitions, F orbitals. Hence, by absorbing the small amount of energy that is from the visible lights, they can go from ground state to the excited and within some fractions they can come there to its original position. In the same way they reflect the light, it emits the light. So FF transitions are much weaker and narrower than those of the DD transitions. So here electrons goes from F to F orbital, ground state to the excited state. So it is called as the FF transition. This makes the colors of the lanthanides complex far fainter than those of the transition metal complexes. Here we can see some examples are there, they are showing the different colors. So that lanthanide is having unpaired electrons and they can absorb the light from the visible region, then and then only they can show the color. Then consequences of the lanthanide contraction. When we see the lanthanide elements are there, all the electrons are having the f orbital and they are entering only in the f orbital, and because of that the atomic size going on shrinking. So that phenomenon is called as the lanthanide contraction. So because of the lanthanide contractions, we can see the consequences. The first one is that the separation of lanthanide elements, because they have the similar size. If the elements have the similar size, how can we separate? No, so this is the first consequences. There are difficulties in the separation of the lanthanides. Second one is the basic strength of the hydroxide. Basicity is nothing but easy to lose the electrons. But now here all the elements having the similar size, then it is very difficult to explain the basic strength of the hydroxide. And here in this chapter we will get the lanthanide hydroxide is less basic than the lutetium hydroxide. So basicity going on decreases. Then the similarities of the second and the third transition series. That is again the similarities between the lanthanum and the post lanthanums. Because the chemical size is same, then the properties is depends mainly on the atomic size. So atomic size will be same, the properties will be same. So this is the third consequences. So these are the consequences of the lanthanide elements because of the lanthanide contractions. Then method of the separation of lanthanides. Now earlier there were so many procedures were used, or we can go through the precipitation method or fractional distillation or complex formation. These are the methods which were used for the separation of the lanthanide elements. But it was very tedious and time consuming methods, and because of that now the newly developed, that is the ion exchange techniques. This method is very useful to separate out and to purify the lanthanide elements from each other. So the technique on which this method is based is that the atomic size of the lanthanide elements, that is the speed of the exchange of ions. So mostly we can use the positive ion exchanger for this method, and we can use the EDTA or HEDTA such as a complexing agent, and then we will form the complex with that metals, and because of that we will get the lambda values will be greater than 1 or less than 1. So if the lambda value will be changed, then our separation factor alpha will be less or more than unity, then it will be get the better and proper separation and purification. So ion exchange method is very useful for this purpose. Then we can see the application of lanthanide elements. The application, the lanthanide elements are used. It is having the variety of the applications we can use anywhere. The first one is that the application in the glass polishing and the ceramics. Now the glass and the ceramics, these all these products we are daily used, and for that, for polishing purposes, or glass polishing or the ceramics, we can use the lanthanide element. The second one is in the nuclear chemistry. We can see the catalytic applications, application in electronic industry, application in medical field, application in developing technology, magnetic application, and in a life science also. So these are the applications of the lanthanide elements. Thank you.